Lecture 72 on arc length. So how do we calculate the length of any arc? That's what we're going to derive right now as a formula. So let's estimate the arc length from A to B using three different distances using straight lines. Now a straight line, we can find the length easily using Pythagoras. So let's say that the height here is dy, which is the change in y, and then this horizontal distance here is dx, which is the change in x, okay? So again, in order to find d1, we can use the Pythagorean theorem. And so we would get dx squared plus dy squared equals d1 squared. And then in order to get d1 alone, we would take the square root, okay? Now, remember that we know what a derivative is. The derivative is also defined by dy over dx. So we're going to solve for dy, meaning that it's equal to f prime of x times dx, and then we can substitute it into this formula, okay? Now what we're going to do is we're going to simplify by adding this squared, distribute that squared to both terms, and then we can factor out this dx squared, meaning that here we're left with a 1, and in the second term we're left with the f prime of x squared, and then this dx squared is on the now multiplying by that term, okay? Now that we're multiplying, I can simplify the square root and the squared by taking the dx out of the square root, okay? So if we were to do that same thing with each of our distances, we would add up all of those distances from 1 to n, depending on how many distances we used of that formula there, okay? And we know from calculus that if we were to let the limit of those number of distances go to infinity and then add all of them up, that would be the same as the integral from a to b of that same square root of 1 plus f prime of x squared, okay? And that is the formula that we'll be using for the arc length. So make sure to write that down. So corrugated material, what is that? Corrugated material looks something like this. It's basically taking a flat piece of material and bending it into a sine wave, okay? And we typically use corrugated material like this because it's much stronger than flat material. So let's do an example with corrugated metal. This metal here below can be modeled by the function y, notice it's a sine function, with an amplitude of 1.35, which is this value right in front of the sine, and a period of 10.67. How do we get that period of 10.67? Well, 2 pi divided by the period should equal this value in front of the x, okay? So we're given that the period is 10.67. How many centimeters of flat metal are needed in order to make each period of corrugated metal? We can use a calculator here, okay? So first thing we need to do is find the derivative of our function. Again, we have a calculator, so you can find it in the calculator, or you can also find it by hand. So that's our derivative. Make sure to use the chain rule on the inside there. And there we go. We simplify it just by multiplying these two together. And now we need to find the arc length. Well, if we were to look at a graph of this function, again, we know that it completes one period, meaning one cycle, at 10.67, okay? So again, in order to use our arc length formula, we need to know our bounds of our integral. So it will start at 0 and end at 10.67. And then we're going to plug in the square root of 1 plus the derivative squared. Okay, notice that just the derivative is squared there. So 1 plus the derivative, which is what we found right here, and we square that. Again, we have a calculator, so we can find our definite integral inside of our calculator easily, and we get 12.196 centimeters. So that's the amount of flat material that we need to make this corrugated metal. Okay, now let's find the length of a cable. So if a flexible cable such as a telephone or power line is suspended between 2 points at the same height, then it takes the shape of a curve with an equation called a catenary, okay? Where A is the height of the lowest part of the cable. So here are some examples of the cables that we're talking about. And this is the equation of the catenary, okay? So again, it's this type of curve here, all right? And again, it says that A is the height of the lowest part of the cable. So the lowest part right there or the lowest part right there. So let's do an example. Electric wires here suspended between two towers from a catenary. So we can see this figure are modeled by the equation y. Again, remember that this equation here is the same equation as we saw before. You're not going to need to remember that. It will always be given to you. And it's between -20, which you can see that's where this tower is, and 20, where x and y are measured in meters. Find the length of the suspended cable of the towers that are 40 meters apart. So again, what we're trying to do is we're trying to find the length of this cable. So first thing first, let's find the derivative of our function. In this problem, you are going to need to review quite a few topics that we've talked about in calculus, and we do not have a calculator, so we're going to have to do all of this by hand. So the first thing we do is we find the derivative. This constant we leave out in front. When I take the derivative of e to the x over 20, we need to make sure we use the chain rule here. And then same thing here, and that negative is going to also make this negative out in front. We distribute the 10, and so we get the coefficients of 1/2 and -1/2. Now we're going to find the arc length. So we're going to plug it into our formula. Again, our bounds here are going to be from -20 to 20, and we want the square root of 1 plus the derivative squared. So this is where we're going to do a lot of review, okay? So the first thing we would need to do is we would need to square this out, okay? When we square that, that perfect square, we're going to get three different terms, okay? So 1 over 2 e to x to the 20 times itself is going to give us 1 over 4, and then that would give us ex to the 20 times ex to the 20, which means that we're going to have to add those exponents, which is going to give us x over 10. Okay, if you need to pause and do that by hand, you can do that. Then we would multiply these two together as well. Well, when we do that, you're going to see that our middle term will get -1/2, and then we multiply this by itself to get 1/4 e to the -x over 10. That's similar to what we did at the beginning. Then we're going to simplify these constants, the 1 and the -1/2. And now we can actually factor this as well, okay? So we can factor that perfect square. So how do we know that this is actually a perfect square? Well, the way that we can identify it is I know that 1 and 4 are perfect squares, so I could take the square root of each of those, and so I would get 1/2, and then my middle term is also 1/2. And then I could also write these exponents here with a squared. And how would I do that? It would be written as x over 20 squared, and again, x over 20 squared, the -x over 20 squared, okay? So that's going to help us to factor it. So that's why we get 1/2 e to the x over 20 plus 1/2 e to the -x over 20, and that is now all squared, okay? If you need to review that, you can pause the video now and you can take this and you can square it by hand, and you'll see that this is what you get, okay? Now, after all of that work, now we can cancel this square root and the squared, and then we can take our integral. So when we integrate here, we're going to have to use u substitution, so that u equal x over 20. So you're going to have to, you're going to get a derivative of 1 over 20, which means you're going to have a 20 in front. Again, this is a review of u substitution. So when we take that integral, you're going to get that 20 over 2, which is going to give this coefficient of 10, e to the x over 20. Same thing with the second term, use u substitution. And then we need to plug in 20 and -20, okay? So plugging in 20 here, we're going to get 10e, and then we plug in 20 here, which is going to give us the -1 exponent. We plug in -20, same thing, and we simplify. And at the end, I did use a calculator to estimate, but if it were without a calculator, this would be our final answer there, okay? Last example. how do we find arc length with Riemann sums, okay? So not always are we going to be given a function. Sometimes you're just going to be given some data points in a table. So this table below gives selected values for a differentiable function f and its derivative. So this is the function value, this is its derivative. Using a left Riemann sum with 3 subintervals of equal length, approximate the length of the graph of f on the interval from 2 to 11. So the first thing is that we know that all of these have an equal length of 3, and we want to use left Riemann sums to approximate the length of the graph, okay? So how are we going to do that? Again, basically what we're doing here is we're approximating this integral, okay? But we can't actually find the exact value because we're just given some data points. So what we're going to do is we're first going to find the length of this subinterval right here. And the way that we're going to do that is we're going to find first the dx, so the horizontal distance would be 5 minus 2. And then we're going to use our values of the derivative here. Again, only the 3 because we're using the left-hand side. And that's what we're going to plug in here. The square root of 1 plus that derivative, in this case is 3, squared. Okay. Then we do the same thing on the next interval. So we would do 8 minus 5. And then we would, again, approximate using the square root formula. And the derivative of using the left side would be the 2. And then the last interval would be 11 minus 8. And then the derivative is that 0 squared. Okay. Then we simplify all of that, and that's our final answer. So for some of the answers, especially on the test, you're going to need to remember your Pythagorean trig identities, specifically sine squared x plus cosine squared x equals 1. If you were to divide these all by sine squared x or cosine squared x, you can derive these other two equations. And some of the multiple choice answers are going to require these Pythagorean trig identities to simplify your answer. So let's say, for example, that we got the square root of 1 plus tangent squared of x. We could rewrite that as the square root of secant squared, and then the square root and squared cancel to just get the integral of secant x. Okay. Today's classwork is activity 72. Make sure that you remember the formula for arc length.